So for the workshop is quite good because it's practicing the rules of logs, okay, combining exponents, combining powers. Make this bigger, combining powers, and then we have here solving R. So isolating R, how do we get rid of the base 10? And then here is for logs. How do we combine logs and how do we get rid of the logs? And then this is quite sort of a more advanced questions of manipulating logs in the context of worded problems. Yeah, and question number 5 as well. We don't have, okay. Yeah, how about just 10 minutes of going over the worksheets, and then 10:30 as usual, we'll look at the solutions to the questions. You happy with that plan? Yeah, I'm sorry you only have 10 minutes, but yeah, this is, yeah, okay, good. All right, so 10 minutes, look at the worksheet, attempt some of the questions, and then at 10:30, we will look at the answers to some of the questions. Okay, so for the first question, it's manipulating powers of 10, base 10. Okay, for the first one, you have here a combination of base 10s being multiplied and divided. So when you're multiplying base 10s, you add the exponents up, right? So 10 exponent 2 times 10 exponent 4, you add the exponents of that and then divided by 10 exponent 3. And if you're dividing, you can, so you subtract the exponent from there. So it's equivalent. So you can write it step by step if you want. You can do 10, 2 plus 4 is 10, 6 divided by 10, 3. So that will be 10, 6 minus 3. Yeah, which is the same as what you will get if you added and subtracted all at the same time. Right, so you can do it step by step in the beginning, and then as you get used to it, you can just go ahead and add and subtract using a single base 10. Right, so for question number 2, it's actually very similar to question number 1. So you'll have A plus B minus C. C is in the exponent, C is in the denominator, so that becomes a negative C, or you're subtracting C. Okay, next one, your 10 exponent 3 divided by 10 exponent negative 3, but it's a division, so you need to subtract the exponents. You have 3 minus negative 3. So don't forget to include the negative signs of the exponents if they have a negative sign, like the exponent of the denominator there. So you should have 10 exponent 6 for the answer number 3. Okay. All right, so that was relatively straightforward, I hope. Combining exponents. So it's just either you add the exponents if you're multiplying the base 10s, or you subtract the exponents if you're dividing the base 10s. Okay, for the second question, it's a rearranging type of question. We want to solve for R, and so we want to isolate R. So the first one that's given, 3 times 10 to the R is equal to 100. Okay, so R is the exponent of base 10. And in the lecture, we learned that to undo the base 10, you need to get the log. But notice how there is 3 that is being multiplied to your base 10. So you cannot just get the log right away. I mentioned in the lecture that before you can get the log, the base 10 should be by itself. That means you need to get rid of this 3 that is being multiplied to the base 10, right? And you have a multiplication that's tying 3 to the base 10. So you need to do the inverse operation of the multiplication, which is the division. So you have, which is division. So you divide the left side with 3 to get rid of 3, but you also have to do that on the right side. And 3 divided by 3 is equal to 1. That's equivalent to just canceling out 3 there. And so you have 10 exponent r on the left side, and you have 100 divided by 3 on the right side. So you can simplify 100 divided by 3 if you want, 33.3, or you can keep it as 100 divided by 3. So I'll just keep it as 100 divided by 3 for now. Okay, so now base 10 is by itself. Then you can get the log of that to undo the base 10. So you have to get the log of both sides. So why don't we just simplify 100 divided by 3, yeah? There might be some rounding errors, and that's probably why I want to keep my log as 100 divided by 3, sort of, yeah. Okay, now log will undo base 10, and that because that's a base 10, that will just be equal to r, and then you get the log of 100 divided by 3. Should be 1.52. So if you get the log of 33 points, oh yeah, it doesn't matter. It still give you, if you get log of 33.33, if you did the 100 divided by 3, it will still give you 1.52. Right. Okay, so the key idea here is you need to get rid of anything that's being multiplied or added or divided to the base 10 before you can get the log. Okay, base 10 should be by itself. So the next question, 4r is equal to 16. 4 exponent r is equal to 16. So you have this exponential equation. The base is 4. Okay, even if the base is not 10, to undo that exponential, it will still be the log. Okay, so you still get the log of both sides. Okay, and you can just get the log right away because the exponential equation is by itself. Nothing is being multiplied, divided, or added or subtracted to it. So you can just take the log right away. Now, the log, the base is 4. It's not base 10. So you cannot just cancel out 4 by the log. You now have to use the rule log base a to c is equal to c log a. Okay, so you have to use that rule. So this becomes r log 4 is equal to log, 16. This should be 16. Yeah. Okay, right. So it's different. If it's base 10, then the log can just cancel out the base 10, like in question number 1. If the base is not 10, then you cannot, the log cannot just cancel out the base 10. You have to use the rule. Yeah, and so you have r times log 4. So this is essentially a multiplication between r and log 4. Okay. So to isolate r, you have to undo this multiplication, okay, by dividing with log 4. So you have to do that on both sides. Okay. Log 4 divided by log 4 is equal to 1. So log 4 is just a number. So it's just like dividing the number by itself. or equivalently, those two cancel each other out, and you have r on the left side, and you can do log 16 divided by log 4, which is equal to 2. Right? Okay, question number 3, it's a bit easier because it's again a base 10, and the base 10 is by itself. The exponential function is by itself, and it's a base 10. So you can just get the log right away, get the log of both sides. Okay, and because it's a base 10, that log will just cancel out that base 10. And so you just have r on the left side, and you can do log of 0.03 in the calculator, which is negative 1.5. Cool. All right, and the third one, 3 raised to r is equal to 10 exponent negative 3. So base 3 exponent r is equal to base 10 exponent 3. And you want to solve for r. So, so the exponential equation is again by itself. It's just base 3 exponent r, except that the base is not 10, the base is 3. So you can just do the log right away. And you have to do the log on both sides of the equation. Okay. Right. So on the left side, you have log base 3 exponent r. So the base is not 10. And so the log will not just cancel out the base 3. You have to apply the rule once again. So you have r times log 3. Okay, that's a times. R times log 3. And on the right side, you have now the log of base 10. Right? So you're getting the log of base 10. The log can just cancel out that base 10. So you have a negative 3 on the right side. Right? Yeah, so you see now what's different here. If your base is 10, the log can just cancel out that base. If your base is not 10, in this case it's 3, then you have to apply the rule when you're getting the log of that base 3 exponent r. Okay. Right, so now r is being tied to log 3 via this multiplication sign. So you have to do the inverse of the multiplication by doing the division. So dividing by log r on left side, you have to do the division on the right side as well. Okay. Log 3 is just a number, and then you do log 3 divided by log 3 is equal to 1. So it's equivalent to just canceling log 3 in the numerator and denominator. So you have r is equal to negative 3 divided by log 3. You can just you can put that in your calculator, negative 6.28 for r, for the answer of r. Okay. Right. Any questions here? Yeah, so as you can see, it's really a recipe. And once you get this recipe, this pattern, and you can apply it to any exponential and log function to rearrange that and isolate the exponent. Right. Okay, so the next question, it's now logs. So we've done the base 10, the exponential functions, base 10 and base other than 10. Now for the next question, we're dealing with logs, and we want to solve for x, and x is inside the log function. Okay, so for the first question, okay, So log and base 10, they are inverses of each other. So for you to get rid of log, yeah, so x is inside of the log function. So that means for you to isolate x, you need to get rid of the log function. And log and base 10 are inverses of each other. So for you to get rid of the log, you need to do the base 10. So you have base 10, okay? And the exponent of your base 10 will be the log of 4x. Right? Okay, so the log becomes the exponent of the base 10. Whatever you do on the left side of the equation, you have to do on the right side as well. So you should also have a base 10 on the right side, and then you have the exponent 2. Yeah. Okay, so 10, base 10 and log will undo each other. So that's equivalent. So you can just think of it as 10, base 10 canceling out the log. So you have just 4x on the left side. Okay, and then you have 10 exponent 2 on the right side. Okay. Or you can expand exponent 2 if you want. That's 100. Yeah, if the exponent is positive, you have 2 zeros equal to the exponent 2. So you can simplify it this way if it's easier for you, or you can leave it as base 10 exponent 2. Okay, now isolating x, right? So 4 is being multiplied to x. So to isolate x, you have to do the inverse operation of the multiplication, divide by 4. You have to do that on both sides. And 4 divided by 4 is equal to 1. So that's equivalent to just canceling out 4 on the left side. And you have x on the left side, and you have 100 divided by 4. Yeah. 100 divided by 4 on the right side, or 10 exponent 2 divided by 4 on the right side gives 25. Okay. Okay, so for the second question, you have log x plus log 3 is equal to log 2. Okay, we want to isolate x. X is inside the log function, so that's x there. Okay, we've already seen from example 1 that to isolate x that's inside the log, we have to do the base 10 in order to get rid of the log, because base 10 is the inverse of log. But notice how log x is being tied to log 3 via this plus sign. Okay, so before you do a base 10, the log should be by itself, just like before you do the log, the exponential should be by itself. Like what we did in the first part here, we had to get rid of 3 before we get the log of base 10 exponent r. So it's the same thing with logs. Before you can get rid of this log by getting the base 10, you have to have that log x by itself. Okay. Yeah. So there are two ways of doing this. It's a plus. So log x is being tied to log 3 via this plus sign. So you can get rid of log 3 by doing a subtraction, right? So you can do minus log 3 on the left side, but you also have to do that on the right side. You also have to do a minus log 3 on the right side, so that you simplify this equation as log x. Okay, log 3 minus log 3 disappears, so you have log 2 minus log 3 on the right side. Okay, right. Log 2 minus log 3, it's just a number. In fact, you can just simplify that. So log 2 is 0.3 minus log 3, which is 0.4. It's just negative 0.176. Okay, so it's just a number on the right side. And log x is by itself. So now you can do the base 10 to get rid of log x. Yeah. So base 10 and the exponent is log x. Okay. You have to do that on the right side as well. Base 10 and the exponent is negative 176. Did I? Yeah. Right, so it's a base, the base 10 will cancel out logs. You just have x on the left side, and then you do base 10 exponent negative 1 point. So you do that here. So you can do this base 10. And you can do this x to the y in your calculator. So base 10 x to the y, and you have 0.176 negative. For the exponent, you have 0.6, let me just see, 0.667. Yeah. Right. So you can do it this way. The whole idea of it is that the log x should be by itself before you do the base 10 and get rid of the log. The other method that you can do, so notice you have log x plus log 3, and we have the rule that log a times b is equal to log a plus log b. Okay. So you can simplify log x plus log 3. Log x plus log 3 can be written as log 3 times x. Right? Will be equal to log x plus log 3. Okay. Right? So that the left side will just be log 3, and then you have the multiplication there. Okay. 3 times x is equal to log 2. Okay. Right? And then your log 3 times x is just by itself. So you can now do the base 10 because the log is by itself. So you do base 10 and the exponent becomes log 3 times x. Okay. And you do the log base 10 as well on the right side. The log will cancel each other out. So you have 3 times x on the left side, that's equal to 10 log 2. Yeah, so here now is the question in the chat box. Isn't it log x is equal to 0.667? So here it's from this step of the solution, right? So you have base 10 log x. Okay. Base 10 log x. So the base 10 sort of cancels out the log. Okay, so the log disappears, and that's why it's just x. It's just x now on the left side. Yes. Yeah. Yeah. Yes, you're right, Oksana. So log 2 minus log 3, which is this one here. You can write this as log of 2 divided by 3. Yeah, and you can also do log x is equal to log 2 divided by 3. Yeah, and yes, you're right, x will be equal to 2 divided by 3, and that is 0.667. So you will still get the same answer if you did your method, Oksana, of doing that, of simplifying log 2 minus log 3 as log 2/3. And then, yeah, x will be equal to 2/3, which is also 0.667. Yeah. Yeah, so there are multiple ways of actually answering this, depending on what you're comfortable with. Is which one is easier for you to sort of work through. So in this part here, I remove log 3 by subtracting with log 3. In this second solution I'm doing on the right side, I combine log x plus log 3 into a single log using the rules. Yeah, and then you have here, yeah, which is, yeah, let's just finish what I've started here. So you have 3 times x divided by 3. Then you have x is equal to, so 10 log will also disappear. So I should also like simplify that, because 10 log 2 will just become 2. So x is equal to 2/3, which is also equal to 0.667. Yeah, good. All right. But the idea here is, before you can do the base 10 to get rid of the log should be by itself. Okay, it's not being added to something else or multiplied or divided by something else. The log should be by itself before you can get the base 10 to get rid of the log. And so it's the same concept for the next question, because you have log 3 minus log 2x, okay, is equal to log 12. Right? Okay, so you have x is inside the log, but you have this log 3 minus log 3, 2x. Okay, so you can also do the subtraction, the algebra, the first method I did here, or you can combine the logs. So let's do that method of combining the logs. So you have the rule, log a minus log b is equal to log a divided by b, right? So this one here, you can combine that into a single log 3 divided by 2x, right? Okay, and that's equal to log 12 on the right side. Okay, now the log is by itself. Okay, when the log is by itself, you can now do the base 10, base 10, and then the exponent is the log 3 divided by 2x. Okay, and you also have to do the base 10 on the other side. Okay, right, you have base 10 and the log will sort of get rid of each other. So the left side will now just be 3 divided by 2x. Okay. And then the right side is just 12. Right. And it's now just an algebraic expression that you need to manipulate to isolate x. Okay. So x is in the denominator. It will be easier if you flip your equation so that x is in the numerator you flip it, it will be that way. Right? And then you can get rid of 2/3. So you can do times 3 and divided by 2. Okay. Times 3 divided by 2. Because then 2 divided by 2 is equal to 1, and 3 divided by 3 is equal to 1. Right. And so you have x is equal to 3 over 24, or that is equal to 0.125. Okay, so it looks like combining logs will just give you like a neater solution rather than subtracting or adding. But the whole idea, again, is before you can get rid of the log by taking the base 10, the log should be by itself. All right, cool. All right. Okay, so yeah, so I'm quite conscious of the time. It's 11 o'clock. So if you need to go, you're free to go. But if you want to stay, I'll keep going, looking at the solutions. So we'll have a complete solution to the worksheet, and I'll post the video on stream afterwards. Yeah. Oh, so Hannah, did I answer your question earlier? So log x. Yep. Okay. Good. All right. Cool. Okay. So the next question here is sort of trying to see a pattern, filling out this table. So I'll just do the first row in the table, and you can do the rest of the rows just to conserve time. And for us to be able to answer the follow-up questions number 2 and number 4. So here you have the equation L is equal to 10 times log of P divided by P0, and P0 is given as 10 to the minus 12. So you can just write this equation as L is equal to 10 times, so there's a multiplication sign there, log of P divided by 10 exponent negative 12. Okay. And we're going to investigate what happens to when P is increased by 100%. So increased by 100% means it's doubled. AP is doubled for a range of P values. So first one, when P is equal to 10, okay, the new P is increased. So P is increased by 100% means the new P is doubled. So that will be 20 for the new P. And we want to find what is L and then new L, meaning after doubling P. Okay, so for L, it's just a matter of substituting the value of P in the equation. So you have 10 times log of, when P is equal to 10, so that's 10 divided by 10 exponent negative 12. Yeah. All right, so do the log 10 divided by 10 exponent negative 12. That should give you 13. And then times 10, so that will be 130 for the L. Okay. For the new L, what you need to do is the same equation, 10 times log. Okay, the new P is 20. So it will be the new P that you'll use, 20 divided by 10 exponent negative 12. Okay, carrying out the 20 divided by 10 exponent negative 12, getting the log of that will give you 13.3 times 10. So that will be 133 for new L. Okay, so it's the same procedure for different P values. So this is the equation, you just change the value of P, and you should be able to recreate this. So if P is 20, new P is 40, it's just doubling for the new P. Okay, an increase of 100% is just doubling the value of P. And when you calculate L using the first equation here, you should get something like these values. Sorry. 137, 140, and then 150. Okay, and then for the new P, if you do the calculation using the second equation, you'll get something like this. Yeah, you get those numbers, and you can check that. So where 20 came, yes, it's because you doubled P. An increase by 100% means that you double P. And so when P is equal to 10, the new P will be 20. So yes, so you're right, Hannah. So that's what you put in the equation for new L. For the equation for new L, you put the value for from new value of new P, which is double of the old P. Yeah. Right. Okay, and you should fill up the table like this, and you can do the calculations yourselves and check the numbers if you want. But we can now answer the second question. What do you notice about the difference between L and new L? So if you compare L and new L, so compare these two, notice how new L is 3 more than the old L. Yeah, so for all of these values, notice how you're just adding 3 to L in order to get new L. So new L, do I have space? I'll just, new L is always about 3 more than L, no matter what P is, right? Right, so notice that for any value of P, new L is always 3 more than L. And so can you do, next question, can you do a mathematical manipulation of the formula to explain why 3 is, new L is always 3 more than L? So what changed in the formula? So this is your formula. L is equal to 10 log P divided by 10 to the exponent negative 12. So what changed is that instead of P, for the new L, that here. So for the new L, what changed is that P is doubled. Okay. Right, to get the new L, what changed is this, P is doubled. Okay. So if we manipulate this, equation, we can write this as 10 log 2 times P divided by 10 to the negative 12. Yeah, 2P divided by 10 exponent negative 12. I can write that as 2 times P divided by 10 to the negative 12. And the reason why I write it this way is so that I can use the rule for the logs. So I can use the rule for the logs, log 2 plus log P divided by 10 to the negative 12, right? This rule, log of A times B is equal to log A plus log B. Log B. log A plus log B. Okay. All right. So if I rewrite 2p divided by 10 exponent negative 12 as 2 times p divided by 10 exponent negative 12, I can use this rule to write that as log 2 plus log p divided by 10 exponent negative 12. Okay. All right. And then you have here now 10 being multiplied by the whole term in the bracket. Yeah, and we've seen in our previous lectures that with factorization, if you have a number that's being multiplied to something in a bracket, you distribute the multiplication to each term in the bracket. So that will be 10 times log 2 plus 10 times log p divided by 10 to the negative 12. Okay. Right. And notice how, so if you do 10 times log 2, that will be equal to 3, to 3.01. Plus, notice how this 10 times log p divided by 10 exponent negative 12 is the same as the equation for original L. Okay. Right. So 10 times log p divided by 12 is equal to L. Right. And that's why nu L is equal to 3, about 3 plus L. Okay. So that's why, yeah, in the table, nu L is 3 more than the original L. Right. Okay, so a little bit mathematical, this question here. I would say that this question is a little bit more complex than what will be expected in the exam. But this is just demonstrating some, you know, like rules, log for the rules, and that log 2 is equal to 3. Yeah, and just trying to see the pattern. Yeah. Okay. Right, and then for the last question here. Okay, the decay of a drug in a system is characterized by a half-life. Half-life is the time, so half-life is the time it takes for the drug concentration to drop to half. Okay, the half-life is 100 minutes. So just disregard these dollar signs here. The half-life is 100 minutes. And so, for example, we started with a concentration of 1,000 units. After 100 minutes, that means that the concentration will be down to 500, because half-life means the original amount will be halved after a half-life. So if the half-life is 100 minutes, after 100 minutes, 1,000 will be down to 500. And then after another 100 minutes, 500 will be halved. And then you're down to 250. Okay, so that can be modeled by this equation. It's an exponential equation that's base 2. Okay, and the exponent negative t over tau. So you read this Greek symbol as tau. That's equal to the half-life. Half-life, right? Which is 100 minutes. Okay. N0, this is the original, initial number. Initial or original number. at the beginning of the event. So N0 is equal to 1000. Yeah, tau is the half-life. So initially you have a concentration of 1000 units, and then the half-life is 100 minutes. It showed that this formula produces the expected number at 100 minutes, 200 minutes, 300 minutes, and 400 minutes. Okay. So, so for the first question, we're just substituting the value of t. So t is 100, t is 200, t is 300, and t is 400. So we'll do the first one. When t is equal to 100 minutes or 100, so your equation, yeah, so this one, n bracket t, it just means n is a function of time t. Okay, so it doesn't mean n times t. It means that n is a function of t. So you can just, if it's confusing for you, okay, you can just write that as n. The equation as n is equal to n0 to exponent negative t over tau. Okay, and it doesn't change the equation. Yeah. So this bracket t here, it just means that the population, the concentration changes with time. That's just what that means. Right. So to find n after 100 minutes, okay, n0 is the original concentration, which is initial concentration, which is 1000. And that's multiplied to base 2 and exponent negative. So time there is now 100 divided by the half-life, which is 100. Right? Okay, and carry out the calculations. Yeah. Times 2 exponent negative 1, actually. But you can, yeah, you can carry out the calculations in your calculator, and that should give you 500, which is, yeah, which is what we've predicted conceptually. Okay. And you can do the same thing for when t is equal to 200 minutes. Okay. Yeah, you can also just rewrite this equation because n0 is a constant number. That's 1000 times 2 minus t over 100. Yeah. N0 is a constant number, 1000, the original number of concentrations, and tau is the half-life, which is given as 100. So when t is equal to 200 minutes, you can just substitute. So it's still 1000 for the initial concentration times, okay, base 2 raised to the exponent of 200. The time is 200 divided by the half-life, which is still 100. Okay, and you do the calculations. 1000 times 2 exponent negative 2. Yeah. Yeah. And you can do the calculation for 300 and 400. You should get, yeah, because it's, you'll see now the pattern. It's really just a recipe again. So for 300 minutes, you should get half of 250. 400 minutes is half of 125. Okay. Right. Cool. So for the first question, it's pretty much straightforward. You're given the exponential equation. You were given the exponential equation, and you were given the initial concentration N0 and the half-life tau, and you just needed to figure out the concentration after certain times, 100 minutes, 200 minutes, 300 minutes, and 400 minutes. And so you just substitute the required time onto this time t there and carry out the calculation. For the second question, okay, it's a little bit trickier because it's now asking you to calculate how long. How long meaning you want to find the time t, and t is in the exponent. So calculate how long it will take for the concentration to be reduced to 0.1% of the initial concentration. Okay, 0.1% of the initial concentration. 0.1%. Yeah, we learned, I think we talked about percentages in the lectures about fluids. So 0.1%, that's equal to 0.1 divided by 100. Okay. Yeah, so that's 0.001. Yeah. Yeah, so 0.1% of the initial concentration, 0.1% of initial concentration. Okay. We can translate this statement into a mathematical equation. So 0.1%, that means 0.001 or 0.1 divided by 100 of. When you read off, that means times, and initial concentration is the N0, which is 1,000. Right? So this statement, 0.1% of the initial concentration, will give you the actual concentration. It's 0.001 times 1,000. That is 1. Right. So that means n is equal to 1. Okay. This is the 0.01% of. Okay, right? Yeah. Okay, so this is the first hurdle in the problem, which is probably the most important, is figuring out what the concentration is when it says 0.1% of the original or the initial concentration. So then your equation, n is equal to N0 times 2 exponent minus t over tau. Okay. You can now write this as the n is the concentration, that's 1. Okay. The original concentration N0 is 1,000. Okay, and that's times base 2 exponent minus t divided by the half-life is 100. So your equation looks like this now. So what you wanted to find, the question asks you to find the time it takes for the concentration to be equal to 1. So it goes from 1,000 down to 1. How long will it take for the concentration to go from 1,000 down to 1? Okay, right. So you now have to rearrange this equation to isolate t. You want to find the time t. Okay, t is the exponent of base 2, and hopefully by now we now know that before you can get rid of base 2, before you get the logarithm to get rid of base 2, you have to have the base by itself. So we have to get rid of 1,000. So yeah, get rid of 1,000 by dividing both sides by 1,000. 1,000 divided by 1,000 is equal to 1. And so you have 1 divided by 1,000, 0.001. Okay. And here you have 2 exponent t over 100. Now the exponential function is now by itself. Okay, it's base 2, but it's essentially by itself. Then you have to you can now get the log of both sides. So to get rid of the exponential function or the base, you get the log of 2 exponent negative t over 100. Okay. Now the base is 2, it's not 10, so the log will not just cancel out the base 2. Instead, you have to use the rule log a to the r is equal to r log a. Okay, so the minus t over 10 over 100 comes in front of the log, and you have log 2, applying that rule for logs. And the left side would still be log of 0.001. Okay. Right. Now it's now just an algebraic expression. So you have minus t divided by 100 and times log 2. Log 2 is just a number. So yeah, so log 2 is a single number. You can think of it as a single number. So to isolate t, you can, yeah, like that. So t is being multiplied to log 2. So if you divide by log 2 and you multiply by 100, okay, then you're essentially doing 100 divided by 100, and you're canceling that out. And you're doing log 2 divided by log 2. You're canceling out the log as well. So you have to do that on the left side as well. Multiply by 100 and divide by log 2. Okay. So your equation looks like minus t is equal to 100 times log 0.001 divided by log 2. Yeah, and you can carry out the calculation. This will be, you'll get something like -3. So you do log 0.001 divided by, times 100, and then divided by log 2 is -3. But -3 is equal to negative time, negative t. And so the negative will cancel each other out. So t is equal to 3. And the unit for t will be the same unit as the half-life, which is given in minutes. That was the units given. You can just, oh wait, I think, log, this is not equal to 3. Log 0.001 divided by log 2, okay, times 100 is actually negative 996.6. So your time will be 996.6. Yeah, so it takes 996 minutes, 997, around 997 minutes for the concentration to go down from 1,000 to 1 unit. All right, okay. Any question about the solutions to the workshop problems, or about transcendental functions, or anything else? Yeah, no questions. All right, cool. Yep. If there are no questions, yeah, then we can end the session. The recording will be up on stream as well as the annotated notes. And so, yeah, have a good day, everyone. And I'll see you on Friday for our last lecture for the semester, where we'll learn about sound. Okay.